something that is not very intuitive is dark energy and dark matter. That's very difficult to grapple. Do you have an easy explanation of what these things are?
In particular, what I'm really excited about in the next decade that I know will happen is, the launch of the LISA space mission, which is going to detect gravitational waves from colliding supermassive black holes. I think the pace of refinement of the LLMs, right? So the LLMs happened, you had ChatGPT, and the progress that's happened since ChatGPT came out is just remarkable. So I think I would like to veer kind of close to a black hole, like as close as we can get. So I'm most worried for the young people in my group and in general. We didn't have all of these ways of learning new things. And I think keeping that interest to learn a lot of different things, and that's what I think we should be using the internet for, like milking the internet for. So this is what I mean by kind of serendipity. These connections and things that you don't even know are consciously informing your thinking process.
Welcome all of you. Welcome Dr. Priyamvada Natarajan to the Indian Express. This is a good way to begin the new year, the Indian Idea Exchange series with you. Dr. Priyamvada Natarajan is a professor of astronomy and physics at the Yale University. She's an astrophysicist, which means she studies the evolution of the universe, things like stars and galaxies and how they are formed, how they are changing with time. Her particular interest is things like black holes, things like dark matter, dark energy, things which are esoteric to us, which we don't have much of a grip on, but she understands them fairly well. And one of the several things that she has done during her early years of research was that she came up with a hypothesis for an alternative evolutionary approach for the formation of very massive black holes that sort of explained why supermassive black holes, which otherwise take a lot of time to be there, were found in the early stages of the universe itself. And that particular, that hypothesis now gets supported with fresh data that have come out from James Webb. So that's likely to, change our understanding or improve our understanding of the universe in general. So welcome. Thank you so much for coming here. She's been... You are a Delhi girl,
yes,
mainly.
Yes, absolutely.
She has studied in Delhi before she moved to US in the mid 80s. So do you still consider this your home? Is it homecoming for you?
First of all, welcome. Thank you so much for inviting me. I am really excited to be here, except I cannot recognize Delhi anymore. And I still am a Delhi girl, but I hate this pollution. It's just, it doesn't make you feel happy to be in Delhi, right? So it's really sad. I think we have to fix this problem somehow, right?
Right. So now if we begin with your field itself, considering the very large number of major breakthroughs that have been announced in the last few years, it seems to be a particularly exciting time for astrophysics. If you could tell us why this is happening, what are the kind of new capabilities that we have acquired in the last few years, which is making it possible, and how exciting someone like you feels about this?
Yeah, so I think that one of the exciting things about sort of the frontier of science and technology today is that in order for a field to mature and to be in a golden age, what you really need is a confluence of ideas and instruments. So they have to align and converge in a way that you can open up discovery space so much more efficiently and faster. So what's happened in astrophysics and cosmology is particularly remarkable in terms of timing. It's been happening for the last 10, 20 years. So we've had some fantastic space telescopes, the Hubble Space Telescope, the Chandra X-ray Telescope, and now the James Webb Space Telescope. So these are three very different pairs of eyes that look into the universe in very different wavelengths. And to have them simultaneously look at the universe, we've never had something like this before. And and viewing from space has huge advantages. The atmosphere, Earth's atmosphere, much as we need it, actually causes a lot of perturbation in the light. It distorts, adds kind of distortions in the light. So when we get images, we have to actually do a lot of processing before we can remove that effect. It's very turbulent on small scales. So you need to have imaging in space, imaging and spectra from space. So that, and then in combination with the advances in computing, just the speed and the capacity, the kind of capacity to compute at scale, at the kind of scale to, so we are now able to simulate portions of the size of the universe that are slowly getting somewhat comparable to the observed universe. So the biggest gap has been that we've now observed close to half of the entire night sky in great detail, and we've mapped it out. And because cosmology and astrophysics are a very strange field, right? Scientifically, you cannot do any controlled experiments in this field. So the classical definition, like the Baconian, Popperian definition of science, where you can falsify by just comparing, you'll never have a sample. You can never control an event that happens in the universe. And you are making these measurements sitting inside it. So you're not an outside observer. This is sort of typically in science, you imagine that you have an observer and you have a system that you observe, right? So here we are right in the middle of it. So it makes it very challenging. So the solution that we have had in cosmology is that you do controlled numerical experiments. So you simulate a piece of the universe on your computer. We know the initial conditions of our universe, so we can set it off, and we know gravity is the only dominant game in town. It's not the only game, but it's the only dominant game in town. And you can set it go, and you can see what kind of phenomena you get. And then you can compare something that happens in the real universe to whether you can reproduce it in the simulated universe. Because you know what you had to put in the simulated universe, then you can uncover properties and features of what you see. But there was a real mismatch in the volume of the universe that you could simulate. You could simulate, 1/1,000,000th of the size of the universe. So then you're looking at something in a very tiny volume in the numerical universe, and you're looking at the entire universe where you're seeing a rare phenomenon, and it may never happen in this box. So you may never really understand the physics at a fundamental level because that phenomena that you're seeing, you don't actually see an analog of it happening. So the goal is to try and make this volume larger and larger. So that has also happened with the advances in computing and chip technology and parallel computing. We're now able to simulate a larger and larger portion of our universe. Right? So that's another kind of convergence. And then, of course, for theorists like me, it's the sophistication of the conceptual models that we can build. That's also advanced over the last decades. Astrophysics has always been, a science that has moved at a pretty fast clip because we've always had data. We are sort of the original big data science, right? So I think it's this real convergence of all of these threads that's making this a very exciting time. And I am particularly thrilled to be alive and working at this stage of my career in this field, when there are these three big space telescopes and other instrumentation on the ground that are all just taking off, right? And I think if I had been in the game, 20 years, 30 years before as a professional, I was a student and I was learning, but then, I would have been not quite timed right. But I feel so fortunate and blessed to be doing this now at this time, and to have had the toolkit, right? To have developed the skills and the toolkit to be able to exploit all these data sets that are coming. So I'm also very excited about the future. We are really poised to continue and make remarkable discoveries as time goes on.
It's actually amazing, and especially for people like us who are not in the field, to understand that we know so much about the universe, and most of what we know about the universe, actually just comes from the study of light that's coming from far
Yeah.
away. Uh, and it's actually mind-boggling for ordinary minds like us to be able to understand how much information is packed on those ray of light, and how do you manage to extract all that. So if you could, I mean, it might just take 2 semesters of undergrad to actually follow this, but if you could tell us in brief, this process, how is it done, how is that information, what kind of information that light gives you, and how is that extracted from?
Right. So, I mean, light is sort of our cosmic messenger. And so it's the combination of imaging, so just taking an image in different wavelengths of light. So, the electromagnetic spectrum, there's only a very small portion that is visible to our retinas, right? So there are X-rays, radios, microwaves, so there's a full electromagnetic spectrum. And you can see phenomena in the universe that basically matter is converted into energy by various objects in the universe via different kinds of physics, right? And that energy comes out distributed in different ways across the spectrum. So, for example, black holes. Black holes themselves do not emit any light. The only way we see them is that matter that gets very close to a black hole gets pulled in by the intense gravity of the black hole. It gets sped up. So, if you think of a packet of gas, so ordinary gas, hydrogen, so it would get pulled in and heated up before it crosses the point of no return, which for the black hole is an event horizon. So once anything crosses that, you don't get any more information out. But before you reach there, you get heated up and you start glowing in the X-rays. So that's how we know there's a black hole, because we see intense bursts of X-ray radiation from this matter that's getting pulled in, right? So all the photons, all the light that is coming from this packet of gas is coming out mostly in the X-rays. Some of it is coming in the ultraviolet in different parts of the spectrum. Little bit is coming in the radio, little bit is coming in the infrared. So every object has an unique energetic fingerprint of how much energy will come out in each of these wavelengths. So when you see a bunch of stars, because we now understand the physics of stars, we know stellar evolution really well, and it's all hydrogen and helium. And everything else is very trace elements. They are important, but hydrogen basically rules the universe in terms of ordinary matter. And it's the interaction of hydrogen with energy that we are seeing as these cosmic footprints, right? So you get this fingerprint, it's unique for every object. That's what allows us to pin things down. And the fact that we have these natural laws that help us with causation. We're like, this happens because that physics is happening in that place. So the other kind of slightly complicating but exciting thing about the universe is our universe is actually expanding, and the expansion is accelerating. What that means is the distance. So it's not like, you are expanding into something. It's just the distance between objects is increasing with time fairly rapidly. And this impacts what happens to light rays. So when light rays are being this, cosmic fingerprint, that energy is being sent out. In the meanwhile, space is expanding. So these wavelength actually gets shifted out, gets stretched out because of the expansion. So by the time you detect things, they no longer look like what was coming out. It's still unique, but you have to undo this expansion to really understand what's happening at the object. So for example, if you go out and through a telescope, you look at the night sky. I don't know if we can look through the Delhi night sky now. It's really sad. I was a very avid amateur astronomer when I was growing up in Delhi and involved with the Nehru Planetarium. So you go out in the night sky, when you see a distance fudge, which is a galaxy, you are seeing it as it was million, maybe billion years ago, depending on how far away it is. What does it look like today? No idea. Because you're getting the light, you're getting ancient light, if you will. You're getting the light, you're getting the photons that left that galaxy millions, if not billions of years ago, depending on how far away the galaxy is, right? So we've had to, when we look out and get data, we have a really good idea of the physics of most objects. We know what the fingerprint in terms of energy for a black hole would look like, for stars, for planets that are just reflecting light and not producing their own light. We know what warm hydrogen gas looks like. It's spread everywhere in the universe. It glows. And then we know what really hot gas balls look like in the universe because they all emit in the X-ray. So we have a good idea of the physical processes that produce the energy and the wavelength at which they produce the energy for each class of celestial objects. Occasionally, you have new kinds of objects. So, for example, when I was just starting in graduate school in the mid-1990s, there was a whole class of new objects, gamma ray bursts. So most of their energy was coming out in the gamma rays. And it turns out that, and they were these new objects. Everyone thought these were new objects. So it turns out that the military in the US had already detected these objects in the 1960s. They thought these were they were probably, explosions, human explosion bombs, right, that were going off. They didn't know they were actually celestial because they couldn't figure out they couldn't see it. They were just detecting gamma rays, right? They couldn't place where the objects were. So, and we didn't know about it until astronomers started, so they classified everything. So then astronomers, they started happening very frequently, almost one a day, and this couldn't be an explosion at that point. So everything got declassified, and they realized there were this new class of objects called gamma ray bursts, that most of the energy comes out in gamma rays. We'd never seen an object like that before. And now there's another new class of objects about 10 years ago called fast radio bursts. As the name tells you, they're really fast, kind of, clicking radio bursts that are also quite frequent in the universe. So I think that even though we know the physics, there's still maybe objects lurking that we hadn't imagined are there. But we have a pretty good kind of atlas, if you will, of the kinds of physical processes, and the kinds of radiation you would get from them. But the most intriguing thing is that all the matter in the universe, that is ordinary atoms, the stuff that we're made of, the stuff the stars are made of, is only 4% of the inventory of the universe. And the bulk of the matter content of the universe, which is actually dark matter, 90% of all the matter is dark matter, that stuff actually emits no radiation. Yes. So it has no fingerprint as of now.
No, actually, I was coming about, black holes at least. Even if we don't understand, we have sort of an intuitive, understanding of what black hole can be. And in common conversations also, we have a different sort of an understanding, and we use the black hole word pretty often. Something that is not very intuitive is dark energy and dark matter. That's very difficult to grapple. Do you have an easy explanation of what these things are and why they are important?
I mean, if I had an easy explanation, I would be walking to Stockholm, right? Yeah. So, no, I think they're super intriguing, right? And I think they've been elusive, each of them for slightly different reasons. So all matter, as I said, we understand the physics. So we know how matter and radiation couple, how they interact with each other, and they put out energy in different wavelengths, right? That's ordinary matter, all the hydrogen I was telling you about, right? The intriguing thing about dark matter is we have mapped it. We know how it manifests in the universe incredibly well, okay? And in great detail. But we don't know what it is made of. And what we can infer so far, what it might be made of, it seems very peculiar. It's an equation of state. So all of you may remember from your high school, maybe middle school chemistry, Boyle's law, PV equals nRT, like an ideal gas, the pressure and the volume are related to the temperature. So these are the fundamental quantities, right? So and that's the equation of state. PV equals nRT is the equation of state that describes everything you need to know about an ideal gas and its properties, right? So the equation of state for dark matter, which we believe is our current understanding, is P equals 0. So it's pressureless. And so which means, you get pressure because, atoms and molecules, you get pressure only when they collide. So this is collisionless. It's matter, but it's collisionless. So what that means is you have two dark matter particles. They will never kind of collide with each other. They will get, because they have mass, they have gravity, they will get attracted to each other, and then they would kind of circle, and then they would eventually kind of aggregate just by gravity.
And that's why you can't even detect them, because there is no interaction happening.
There's no interaction with any kind of energy on any wavelength. Not infrared, not X-ray, not gamma rays, nothing. So the only impact is gravitational, which means that this is matter, so it's physical. We believe it's some kind of particle that formed in the very early universe, and there's a lot of it, and that it has gravity. And so it exerts gravity on normal matter. And that's how it was discovered in the first place. So the two key ways in which we've discovered them are the way in which, so every galaxy, even our own galaxy, appears to have sort of a scaffolding of dark matter on which somehow the stars have formed. So when we see the stars in our galaxy, like our galaxy is a big spiral, you see all these big spiral galaxies. When you see that image, you are seeing only 10% of what is really there in terms of gravitating mass. There's 90% is invisible, and that's the dark matter. And it's distributed everywhere in the galaxy. It kind of holds the galaxy together. And the way we know that is because when people started measuring, in particular Vera Rubin and Kent Ford, her collaborators in the 1970s, started measuring the speeds of stars in a galaxy from the inside out. So this was for external galaxies, obviously not for our own. We're sitting in the middle of it. We can't do it. For other galaxies, you start measuring the speed as a function of the distance from the center, which is the brightest collection of stars. And they found that the speed was actually increasing, and it kept going, it kept increasing, and then it kind of flattened out, like it sort of saturated at some level, but it was not zero. So if the galaxy had an end, it would be zero, right? And so the galaxy didn't seem to have an end. It seemed to kind of, ooze on. You start to run out of stars, so you can't make any more measurements. But then you have gas, and if you make measurements in the gas, you still found that, there was some gravity that was literally holding up the galaxy. And so that is how dark matter was discovered. And the other kind of important effect of dark matter, and that came from Einstein's theory of general relativity, is that whenever you have any matter, it will have gravity, and what gravity would do, it would deform paths of light. So the way to think about it, and this was kind of, I'll try to keep this brief. I could go on and on with trying to explain sort of key, cute ideas, powerful, cute ideas in general relativity. But what was amazing about what Einstein did was, Newton was able to tell us how gravity works in the universe. It's a force, it's between two objects that have mass m1, m2, separated by distance. It falls off as 1 over r squared of the distance. So he was able to tell us that. He couldn't tell us why. What is the origin of why? Why do two pieces of mass actually attract each other? He didn't have an explanation for it. We didn't in science till Einstein came along. And he was able to describe gravity as the kind of interplay between matter and the shape of space itself. So the presence of matter deforms the shape of space, and the shape of space, the deformations in the shape of space, actually direct matter to move, right? And so he was able to describe gravity in a brand new kind of geometrical, sort of mathematical way that was super profound, because it could be validated. This way of thinking could be validated. So one of the predictions he made is that whenever you have matter, and you can think of space and time actually, like 4 dimensions, as a sheet, and matter will cause a little pothole in that sheet. The presence of matter will cause a little bit of a pothole. And depending on how the matter is, like if it's a really tiny piece of matter that has a lot of matter packed into it, like a black hole, you actually make a puncture in that sheet. Whereas if you have something like a neutron star that's more dense, you make a slightly deeper kind of divot in space-time. So he was able to show us, therefore, And remember, space-time is, we are all in space-time. There's nothing above space-time. That's the universe. The universe is space-time. That was Einstein's. And all matter is like little pockmarks on this sheet. So it's full of little potholes. And that is our universe. There's nothing above or below. So when light travels to us, it actually goes up and down each pothole. And that deformation tells you the strength of, so that changes the shape of objects that we infer in the universe. It distorts the shape. And it's called gravitational lensing. And so matter acts like a lens, like the lens that we've all played with, those magnifying lenses. So matter actually acts as a lens. So it bends light. And so this light bending, Einstein had already predicted, and it was detected during the solar eclipse. And now we routinely see, and that's what Hubble Space Telescope did. It transformed the field of gravitational lensing. So if you go and look at one of those images of Hubble Space Telescope of a cluster of galaxies, has a lot of dark matter, and you see a lot of bent shapes of galaxies. So that's just lensing. You can pick it out by eye. You don't need any instruments to see it. So I think coming back to the question of, dark matter detection, it's been super challenging. And then 30 years, the particle, because ultimately it's a particle. We need to find out what particle it is, right? So particle physicists have been doing experiments at CERN, at other sort of, underground mines to detect, the gravitational interaction of a dark matter particle kind of going through. So the fact that it's collisionless, right? So dark matter goes through our bodies. There's not a lot of it not a lot of it on Earth. So, it's not doing much to us, but it would just go through without changing anything about us, right? Because it doesn't interact, right? So it's very hard to actually detect. And so in these mines, we've not found anything. But we were looking at very specific candidates. And in particular, we were all fixated on one candidate, which, we all loved because the physics of it was just really beautiful. It was called the neutralino. It was very massive, and we were looking for it and haven't found it. So now we've realized, unlike the drunk who's looking for the lost key only under the lamp that is on, we actually have to look a little further. And so now we've moved on to another class of particles, which is a little bit lighter, but very interesting, also available in the early universe. They're called axions. Right. So now that's the new kind of, the new sort of domain that we've opened up. And could, and of course there are all these speculations, could there have been many black holes that were made, mini black holes made in the very early universe that could be dark matter? Maybe, but they can't explain all the dark matter that we need in the universe. And I often joke, right? People ask, what else could it be? I was like, all the missing objects in your life, maybe, could they be dark matter? Sure, missing socks, yes, maybe, but who knows? Yeah, so we've not yet found dark matter.
But, given the massive increase in observational capabilities, thanks to JWST and other apparatuses, massive increases in computational abilities, also, the new possibilities, the new potentialities unleashed by artificial intelligence and all. What are a few mysteries that you're very hopeful would probably get solved in the next few years, or maybe at least in our lifetimes? The issue that these mysteries finally get solved.
Well, okay, first of all, the future of science is very hard to predict because serendipity plays a very important role in discovery. It's often not acknowledged, but you never know, who might come along and make a connection that is so out of our realm of possibility right now that might just click and solve one of the big, great mysteries. So we don't know. One thing we do know is that Einstein's theory of general relativity is not the final word. That there has to be, we think that this is a belief, but it's a fairly well-grounded belief that all the forces of nature should be integrated in some way. And at the moment, which means that at the moment, gravity is not integrated in the sense that we don't have a microphysics of gravity that's well understood. We understand the microphysics of how radiation works, how electromagnetic forces work, all of that, but we don't, right? So I think in terms of the next breakthroughs, I am really hopeful that, in all three sort of the big kind of pillars in cosmology, which are, paradoxically all, as I said, their manifestation is known, but we don't know what their true nature is. On black holes, dark matter, dark energy, I think they're going to be major breakthroughs. So we're already seeing some hints. So in dark matter, the work of my research group and many other groups in Europe have found that the current paradigm, there are some kind of cracks. So, we are always, as scientists, like working at the frontier, we are trying to see, you have a current model that explains almost everything that we see. We are trying to push the models with really good data to see if it breaks somewhere, if there's a place where it doesn't work. And the reason you want to do that is often the gaps are where you get clues to what the next new kind of deeper understanding might be, or what is wrong, whether you need to refine this current theory or you need to really look for a brand new theory. Those clues come from those gaps. And I've personally been kind of obsessed with those gaps, right? So trying to illuminate those gaps and then learn from those gaps to see what new things you can learn. So I think right now we are seeing a crack emerging in our understanding of dark matter on very small scales. There are mismatches between the data and theoretical expectations of the standard model. And then in dark energy, we all believed that it was some constant component. So dark energy is the energy we believe is powering the accelerating expansion of the universe, as I mentioned earlier. Again, we know how it manifests. It drives the accelerating expansion. We don't know what it is. But we believed that it stayed the same from the beginning of the universe to today. But very recently, there have been some hints, and we've put out a paper, it's not yet peer reviewed, a brand new way to examine potential evolution in dark energy, changing in time. So there have been hints that maybe this dark energy is not quite what we thought it was. And I think with black holes, they are an enigma. And I think there's so many open questions about black holes that I think that are ripe to be solved. That I think in all these three pillars in cosmology, we are going to see major breakthroughs. In particular, what I'm really excited about in the next decade that I know will happen is the launch of the LISA space mission, which is going to detect gravitational waves from colliding supermassive black holes. That's definitely going to happen. I think that the rest, as I said, you never know what can happen and when.
But we are also, and I'll open it up after this, but we are also supposed to be at the cusp of major technology breakthroughs, not just in astrophysics, but in other areas as well. And often, the mention of AI and quantum comes into it, but also other things, possibly, clean energy technologies, for example. Maybe we even fix the fusion problem in a decade or so. And it's often said that some of the control over these technologies and whoever is able to make a headway on these technologies is also going to progress very fast and sort of control the global dynamics going into the next 50, 100 years. Would you say we are actually at the cusp of a sort of a transformational thing that in the next in the next 10, 20, 50 years, probably life as we see it would be very, very different from what we experience now?
I mean, I think that without hyping it too much, I think substantially we have to accept that AI is going to be a real transformative force for society, for science, our daily lives, for the very structure of our lives. And the question is, how do we harness it for good? Okay. And I think it's very clear that in fundamental research, in fields like, any field you take, including astrophysics or cosmology, AI is poised to be transformative. It's just that we can't quite see, given how we've done research for decades, and we think we have a very sophisticated system of understanding phenomena, experimenting, and everything. We can't quite see exactly how it's going to transform the discovery process, because as I've hinted to you already, I kept saying, well, who knows, there might be a young person who comes up and makes this, connection that we can't think about. Um, that last kind of leap of human creativity, intuition, and sort of inexplicable stuff, right? That you have these brilliant scientists who come along who somehow make these connections that were not thought about for generations before them, right? That part of the creative process, that very kind of intriguing, remarkable process, which seems beyond comprehension, right? That how did this creative individual do it? I don't know whether and how long it would take, whether and how long it would take for AI to bridge that, right? And so that's the big uncertainty. So I don't know how it's going to transform that creative arc, but that it's going to transform processes is completely a given. Therefore, the countries that will have global dominance in science and technology will be the ones that can harness AI and this revolution to solve the big global problems. As you said, energy, sort of, renewable energy, new sources of energy, dealing with the huge impact, negative impacts of climate change. So I think this is like a brand new kind of revolution that is rumbling along. And whoever is able to harness this best is clearly going to dominate in science and technology. And I think this is true for fundamental research too. I mean, not just applied things, right? I mean, the thing with fundamental science is that there's a time lag. There's work that's done, research that needs to be done, and for that to translate into something that touches our lives, right? You take the iPhone, for instance, right? And I often give this example. Without quantum mechanics and without Einstein's theory of general relativity, you wouldn't have that iPhone in your hand. There would have been no chip without quantum mechanics, right? And it was thought it was some esoteric, theoretical idea in the 1920s and 30s. And without Einstein's theory of general relativity, there'd be no GPS, there'd be no satellite. We couldn't have launched a single satellite, right? So, but who could have? That time that it took 50, 60 years. AI has the capacity to shrink that. I can't say how, but it's pretty clear that that's another thing. That's another way in which AI can intervene in the discovery process, is in translation and kind of reducing the time that it's going to take for fundamental ideas to be translated into something that'll change our lives, right? And I just think that we are poised for transformations both in the pace of fundamental scientific research, the pace of translation, and the pace of finding solutions. For
and you do believe that at some point of time, AI would become creative enough to be able to ask meaningful research questions? There is no physical sort of barrier, do you think?
I don't know. I think it's hard to tell. It's hard to tell because I think we don't, cognitive neuroscientists are really trying to figure how we do it. How this system that we know and that we can experiment with and that we understand that is not a black box, people have been trying to figure out like what is really going on with creative processes when human beings come up with it, right? So I think there's a real race to try and understand what is it that you need for creativity? What kind of, and I think that AI has not cracked that problem yet. But I don't know, the pace at which things are going, I see no fundamental reason to say AI will never do it. That's all I can say right now, right? But I can't conclusively say it will do it in 5 years or 10 years or 1 year. I mean, I think the pace of refinement of the LLMs, right? So the LLMs happened, and you had ChatGPT, and the progress that's happened since ChatGPT came out is just remarkable. It's just remarkable, right? And all of you would have experienced just going there and trying to
use it
figure
every
stuff
day.
out.
Yes. Yeah. Right. So I'll just open it up if you have any of the questions, please identify yourself and then.
Yeah, you've been using telescopes since you were a child. And these three that you're so excited about, at least, you feel that it's a very exciting time for an astrophysicist to be around. Have you used all of them?
Yes.
And where?
Yeah, so I mean, with the space telescopes, the way it works is that you make a proposal for getting time on a telescope to actually look at a patch of sky that you want to look at. And so you submit it, that proposal is evaluated by peers, and if it gets picked, then they will point the telescope and gather the data for you and then tell you the data is there, you download it, and you can see it on your computer. So yes, I have applied and successfully gotten time on all three space telescopes, yes. And it's super exciting. So, but you know what's happened is that with the space telescopes, obviously you're not looking through anything. I mean, it's in space. So computer commands are sent to the telescope to change and say, okay, Natarajan's proposal said we need to look here. So they will turn and it will look there for the amount of time I asked for, and it'll turn back and go look at somebody else's proposed time, right? So even ground-based telescopes, right, which I used to play with small ones, right? And the big ground-based telescopes, there are some really spectacular ground-based telescopes in Chile and Hawaii, for example. So I have been to those telescopes, but we no longer actually look through them anymore. They're all robotically controlled, and we sit there. Even if we go to the telescope, we're sitting and we're looking at a computer screen. And we're looking at a computer screen on the patch of sky that the telescope is actually looking at. So that romantic idea of sitting in a cold dome, and looking through, that's kind of, nostalgia now. It's not really done professionally.
Anura?
I wanted to know if you did not have any, fuel or velocity constraint, what is it that you would love to study in space?
I see. Oh, you mean if I could, if the speed of light was not a constraint? Oh my God, yeah, this is a good one. I think that's a great one for imagination, right? So I think I would like to veer kind of close to a black hole. Like as close as we can get. I don't know. I mean, I think I might kind of want to get, we've gotten close enough to the event horizon. So you may have all seen that image of a donut of light that around the black hole of M87 star. So that image, light emanated from about 2 to 3 times the event horizon. So we can skirt a little closer. And I think personally, I would want to experience kind of intense gravity. Although I often say when I'm asked that, I'm quite vain about my hair. So the thing about falling into a black hole, right? If you go head first, you'd get stretched out, right? Yeah. So, this will all go first, right? So I don't know, do I want to go feet first or head first? You'll get spaghettified, right? So I don't want to get spaghettified, but I would like to lurk kind of close and to see if we can learn some. Does it hold a secret that we don't know yet, right? So.
Hi, Shan this side. I have 2 questions. So you were saying that you test the limits of the existing models and to see where they break, right? Would an LLM model be or an AI system be useful in that to test where the model breaks and to figure out where the next pathway lies? And secondly, you are at a Yale lab, I presume, right? Yeah. What would it take to set up a lab like that in India? What is the constraint? I mean, is it money? Is it access to researchers? What is it?
Yeah, so the first question, I think LLMs don't quite have the structural features that would allow you to do the kind of confrontation of theoretical ideas with data quite yet. But that's where things are going. And it could get to be refined enough to be able to just take large amounts of data and start confronting. So one of the things we do when I say we kind of cross-match and to see if you find any gaps is we are looking for, say, in a simulation, sets of correlations between quantities, right? And look for the same correlations in the data and see, are they produced, right? So what AI can do, and LLMs and other more sophisticated machine learning techniques can start to do and have started to do now, is to find higher order correlations. correlations that we have not yet, because it's vast amounts of data that it can chuck through and try to find, right? And the issue is that when AI or machine learning finds a correlation, we don't actually know if there's a causation to it. So in physics, we have laws, so we can link causation to correlations. So that's the current kind of handicap with AI, that not all correlations are causation. So I think once we figure out how to do that mapping, it will really do what you were saying, that we can start confronting, and it should do it much better than we can. As for the second question, I think the kind of outfit that I run, right? My research group has 7 people, so I'm a theoretical person. So I need a lot of computing. So that's not a problem. That can be reproduced in India. I think the thing that's missing is the ecosystem, the research ecosystem that is there, the kind of that's established in places, especially in the United States. For the last 30, 40 years, the United States has dominated fundamental science and technology, right? And the reason for this is the existence of many research universities in which there are researchers who run research groups, very constructive competition, as well as the ability to attract the best talent from around the world to come. So in my research group of 7 people, I have 5 nationalities, right? So this kind of, the ability to tap top talent from wherever, the ecosystem where there are lots of different groups with whom you're collaborating and competing, right? And the kind of infrastructure that is very promptly provided. There are no great delays there's a lot less bureaucracy in running a research lab and getting what you need for research. Like I need access to, high performance computing. So that's already a tiered system in the United States, right? Some of my computing can be done on my desktop today, but then a lot of the work that I do needs more sophisticated. So we have a rack. We've built our own fast computer cluster that we need. And then the next level of computing that I need, there are national facilities. So I can prototype a calculation on my desktop, then scale it up on my cluster, then scale it up and submit it to the national. So all of these things are really streamlined. And that's what I mean by ecosystem. Yes, you need money, but you also need a lot of enthusiastic people to set up and maintain this research ecosystem. And that's what I think a lot of countries like India have a real opportunity right now.
So let me actually ask you a follow-up question on that. Now,
Yeah.
supposing there's already this talk happening in India about getting scientific talent back,
Yeah.
or even like attracting people here, not allowing them to go, allowing as in create incentives here for them
Right.
to be here. So if that suggestion ever comes to someone like you,
Yeah.
why don't you come back?
Yeah.
What are the considerations that would weigh on your mind, both positive and negative, but going back? I would guess pollution would be one, especially if you're asked to
hugely
come
today,
to Delhi.
yeah.
But what are the other considerations that would weigh on your mind? And also a related part is, does it even need a scientist today? Does the scientist need to be located at a particular geography to be able to do the kind of science? I mean,
Right.
can there be a sort of similar results? Can it be obtained, say, just by collaboration between, say, a
Totally.
TIFR and Yale?
Yeah.
So if
Yeah, so I think, I'm coming back to the question of, for someone like me who is now, pretty much, I left India after high school and, pretty much became an adult and grew up in that kind of research environment. I think the research ecosystem, that not being as well set up as it is in the United States would be a big kind of handicap in kind of wanting to come back and set up here. The thing that's a big plus is the talent. There's no lack of talent in India. Incredibly brilliant kids, right? So I think that it's the intellectual research ecosystem that is not quite in place. The kind of extensive collaboration and constructive competitive collaboration where you're ambitious, you take risks, and there's a mindset. And I think we need to shift into that mindset, and we haven't done that yet in our scientific establishment. We have fantastic institutions, we have brilliant people in those institutions, but there's a slight kind of impedance mismatch in terms of setting up what I think could be an incredibly productive and very successful research ecosystem. The other thing is, as you pointed out, right, at some level at this moment in history and of technology, it doesn't matter where you are, but the interactions matter, right? So I think interacting, collaborating. So a lot of the kinds of advantages you have being in the United States, right, is that every summer I go to the Aspen Center of Physics, where all kinds of people from around the United States and Europe are there, top people. And there are workshops in different fields, different subject areas in physics. I go, I learn something new, I go sit in a workshop on condensed matter, which is not my field, and I learn something new there. I talk to some people and I start a collaboration. And I import something into astrophysics that was not part of our lexicon, right? And so there's the institute in Santa Barbara. It's called KITP. There are month-long programs, and we all show up and we go learn from. So it's this kind of continual kind of stoking of curiosity, collaboration, competition as well. And you need these catalyst points, these places of community where people come together, learn from each other. They compete, they spar, they debate, all constructively. Of course, there's a destructive side to all of that, but I think those kinds of things have to be part of the ecosystem. We don't quite have that. And I think part of it is, since you did bring up pollution, I think part of it is that, the demands of day-to-day life in India are still really tiresome, and we've got to somehow move that up a little bit, right? And I remember this, growing up in India before I was a professional scientist, right? My father was an educationist. My mother was a professor, an academic, a sociologist, right? We lived in South Delhi. We were well off. Every day, either there wouldn't be electricity for 1 hour or something, or there would be pani nahi aaya aaj, or something, something else in your external environment needs attention. And it's unanticipated, and it's every day, right? And I think things have become better than that. This is my memory from like 30 years ago. But I still think there's something wearing down, like this pollution, for example, right? I think it's just wearing down. And I think, we as a society have to say, look, we've got to take care of some of these basic things that are really impair our ability to just function, let alone be creative and all of that, right? So, but I still think that the promise of what can happen here is just tremendous. Just because the talent is here. You don't have to, like in the United States, talent came from everywhere to there. In India, there's enough talent to tap from within to really build. And I think there are some really great institutes right now. And the future is really promising. I think that what would be great is if there was more respect for people doing science in society. And, we've moved to a society where your monetary worth has become too important. And I think we need to pay scientists to be able to live well so that it's a good and profitable from the personal point of view career choice. And I think we need to respect them. I think in society, I think in India, we're like obsessed with movie stars, sports people and entrepreneurs who become billionaires or whatever. And I think, yes, there's a place for admiration for all kinds of achievement, but I don't think that we are valuing, the producers of knowledge across fields as much as we should.
Samiksha? Yeah. Ajay, yes, the mic.
Hi, ma'am, my question was regarding how science fares in the right kind of environment, and you spoke about setting up labs, etc. My question was relating to the administration that scientific campuses are functioning under right now. The first Trump administration saw denialism on the Paris Climate Agreement, COVID, and how it tackled the COVID response. Second one has stepped up its efforts against vaccines that we've seen. How does it tangibly affect campuses like yours, labs like yours?
Yeah.
That is one question.
Reduce funding.
Yes, reduce funding, exactly.
Yeah, exactly. So
What
I
have been the tangible impacts and doubts? And slightly diversion one is the second question. Your domain also is adjacent to the issues regarding life on other planets. You try to help other scientists and other domains regarding how the new stars and planets can be identified and discovered. Could you please share your thoughts on this?
Sure.
Extraterrestrial life.
Yes. So first, on the question of what's currently happening in science and technology funding in the United States. So right now, there's been a real shrinking of funding for many essential fields that I think is going to be really detrimental in the long run. In my own field, we've been fortunate to not have any dramatic cuts yet, but we have delays. So we have a lot of uncertainty. We don't know what the budget of NASA and the National Science Foundation are. The National Science Foundation does not yet have a director that has been appointed, right? So I think that this uncertainty and this prolonged uncertainty will have really damaging effects on early career scientists. So if this uncertainty goes on, and I see my own students who are now on the job market looking for faculty jobs, universities are trying to manage and hedge how to handle the changes in funding, and therefore a lot of them are not hiring. So they've all they're sort of very cautious. They are waiting and watching to see what's going to happen with federal funding, right? So a lot of young people, early career scientists, are most likely brilliant people who have been trained, whom we've invested a lot of time and energy in training, might leave and will go on to do other things. And of course, other fields will benefit, whatever. But I think we stand to lose a generation of really brilliant people because 3 or 4 years of uncertainty translates into a whole generation of young people. So I'm most worried for the young people in my group and in general, the early career scientists. So let's hope that many of these delays at least get sorted out. As for what is really going to happen with other fields of research in health, etc., no idea where things are going. They're not going in a great direction, that's for sure. And many of us are really alarmed that this might be a time when, the US enjoyed dominance in science and technology for so long that it might actually start to lose. And that, we need to understand in the United States, they need to understand that fundamental science is the driver of the economy, even in the AI age, right? Without fundamental science, we're not really going to dominate. Just dominating in AI and quantum computing will not make you a scientific superpower anymore. And then the scientific superpower has to have basic sciences. And I think that many people are making that case. And let's hope they're successful and some of this uncertainty gets resolved with renewed funding for us.
So before we go on to the extraterrestrial thing, I just wanted to include a follow-up here. With the government sort of withdrawing, and this is particularly true for the United States, but when the government withdraws, it opens up space for, billionaires to, try to fill in the gap, and we have seen that with SpaceX, doing sort of very promising innovation and technology. How do you see that sort of dynamics? Is it a positive sort of thing that more private players coming into actual R&D?
So I think that, the post-World War II model, the Vannevar Bush model of federal funding for science and technology, which is what has propelled everything in the US so far. It's very clear that the federal government needs to be involved in funding science and technology. The problem, and yes, there is room for philanthropists and private foundations and so on. But the point is that, ultimately, philanthropy and individual billionaires, right, they have their pet causes, right? So if you want to solve the diseases of any of your favorite pet billionaire's grandma, then you're in luck, right? Because you will get funded. The point is that those may not be the diseases that are killing the most children in the world, right? So I think it's about priorities, about intellectual priorities. I worry a little bit about intellectual priorities when you have individual philanthropists, unless, of course, they see it now as an opportunity to make an alliance and start stepping in the way that the federal government did in terms of peer review, figuring out which ideas are interesting and decide to fund them, rather than come with a preconceived set of scientific directions that they want to fund. So I think partnerships are possible, and probably it's time for that in the US, for changing this funding model with more input from private philanthropists. But I think we can't turn over the entire research and development enterprise over to that. Only because of the long-termism versus short-termism in terms of the mindsets, right? Corporate players have a very short timeline, and fundamental research, as I mentioned earlier, right? The timeline is unpredictable. How long it would take for a breakthrough or a discovery to translate into something that would into real impact on our lives. So you need an investor who is invested in the long term and is willing to wait out for returns in the long term. So I think you need that balance. So perhaps, philanthropists who are willing to operate in that mode can really sort of pick up the slack in the federal government. But I don't think that we can write out federal funding in the United States.
And on Nikhil's question on extraterrestrial life, is there hope beyond the statistical argument that is there, that even if there is 1 in a billion chance of life emerging, I mean, obviously there are so many possibilities that it will probably be somewhere.
Yeah. I think, obviously, I can't tell you anything about what I believe are the chances of finding, life. But what is very clear to me is that, yes, there's a statistical argument, but also that we need to not be so fixated on our anthropomorphic notions of life, right? So, Stephen Jay Gould famously pointed out that even on Earth, if you turn back the tape of evolution and run it again, you may not end up with humans that look like us, because there's a lot of randomness that is an integral part of evolution, right? So I think we should be less fixated. We need to get less fixated with life, being defined in terms of human life, and we should be open to all kinds of astrochemistries, right? There could be other life forms that we don't imagine, that don't look anything like us or anything on Earth. So that's all I can say. That I think that if we do that, I'm sure we will find
maybe there's a life form that looks like a rock, or we
I
can't.
don't know. So, historically, we've had very strong intellectual traditions in science, in astronomy, in mathematics, where, our ancient wisdom, at least the texts that we have that have survived, we are able to see that there was a very, very sophisticated understanding of the kind of openness of mind that you needed to have to make progress in understanding and making sense of the physical world. So, for example, the Indian ancients kept alive this idea of the possibility both of a geocentric universe and a heliocentric universe. They were both permitted, right? And so that was a certain kind of openness. They were both radical ideas, sort of an openness to both those radical ideas. And so I think that kind of mindset of being open and willing to change your mind, that kind of mindset we need to develop. So these are small things about society and culture, features of a society and culture that actually translate into much bigger things. And it's one of those strands that gets into research ecosystem. And of course, funding, right? I mean, sustained funding. not funding at the whims and mercies of some cycle of political cycle or whatever, but sustained long-termism, long-term funding. The other thing in the reason I say that the research system ecosystem isn't quite there is that we haven't shifted out of the scarcity mentality. So after India became independent, obviously, I think it was a brilliant choice by Nehru and Baba and others to pick certain scientific areas for investment that appeared to be luxuries at the time. But they realized that these are sort of future areas that could make a fundamental difference to society.
The DA and space.
Exactly, yeah, yeah. So, and I think that so scientists, research scientists, because we didn't have as many resources to put into fundamental science, they picked directions for working that required pencil, paper, and not too much of sort of expensive technical equipment and infrastructure, right? But then India has changed. It's a prosperous country now. It's starting to be prosperous and even more abundantly prosperous. And funding to sciences has really gone up. But I think it's still not high enough as a function of our GDP. It should be much higher. And I think there has to be sustained high level of funding. And when that happens, right, we shift from that scarcity mentality to one of abundance. That's another thing that feeds into the idea of the research ecosystem.
Harish?
Yeah, ma'am, as an astrophysicist, how do you view climate change? And human-made, anthropomorphic.
Yeah, I think that not just as a scientist, but as any responsible citizen of the world, we all know that the pace of climate change has been accelerated by human activity, and we have been deeply impactful on the planet. Our collective extractive behaviors of resources, Earth's resources, have caused and accelerated climate change. But I also believe, as a techno sort of futurist, that the solutions are probably going to come from science and technology as well as our own behaviors. So we obviously have to become more responsible in our use of resources, but also the solutions for cleaner energy are going to come from science and technology. I seriously believe.
Asking from an astrophysicist.
Yeah, from an astrophysicist's point of view, from any scientist's point of view, from anyone who looks at the evidence and tries to understand what's going on, it's inevitable to understand and see, literally witness that climate change and its pace has been accelerated by human activity.
So
I don't have any particular deeper insight as an astrophysicist other than as a scientist being able to evaluate. But I think any citizen can actually evaluate that.
Shubhajit.
Yeah.
Shubhajit this side. You mentioned a few questions, maybe interrelated. You talked about the importance of serendipity
Yeah.
in science, and if you could give example of how it can sort of change the course of sort of scientific knowledge and new frontiers. That is one. The second is you are an established scientist now, but for a young student of science in India, in college or a school, what would you want them to think about, when they are pursuing the scientific sort of knowledge or general knowledge systems? What would you tell them?
Okay, in terms of serendipity, like the kind of role that it plays, right? Perhaps the best example I could give you is something from my own work. So, this idea, what I had grown up reading in textbooks from the work of Subramanian Chandrasekhar, about how stars, very massive stars, live their life out and then they explode and they leave behind a black hole. And that's how black holes form, right? And I think that when the data started to show that there were many, many really massive black holes in place in the very early universe already, when there wasn't much time to grow from one of Chandra's little black holes to a black hole that is 1 billion times the mass of the sun within 1 billion years. So we were starting to see the 1 billion years after the Big Bang. So then it was very clear that something else kind of, you needed possibly. How could you do that? Either there's some physics that we don't know where you can force feed a black hole and make it amplify its growth really fast, right? Or the other possibility was that maybe there are just other ways to make a black hole. Right? So in my own thinking, I have to admit that I know it sounds really cliched, example of having a deep thought in your shower or whatever. But I really did feel it was clear to me that there had to be, I was convinced somehow that there had to be more ways to make a black hole. And so then I set about trying to say, let me forget about whether it happens in our universe and where it'll happen. Let me just look at the physics, and I've learned my physics well. Let me see what kind of physics do I need to have to make a black hole. I need to get a lot of matter into a very tiny place, right? Very quickly. That's the time constraint, right? And because I was doing my PhD in England, I had gotten into the habit of taking baths, right, sitting in the bath. So you pull that plug out of the bath, and there you see a process that happens really fast, and a lot of water goes down, right? So I was calculating like how many gallons of water were in that, how much time does it take for it to go down, and I looked at the gutter through which it goes, right? Tiny 6 holes. It's really, really fast, right? And it was that pressure and gravity that somehow you pull that. It takes effort to pull that plug, especially when it's full. Now you'd have to. And so that really did get me thinking. Okay, forget about. Just see what physics you need. So now I was like, aha, here's an example. I wouldn't have thought of this, but yeah, you need you need pressure. You need something to very rapidly move material into a vortex. Clearly, the vortex is the fastest way to funnel material in, right? So I think I had seen that, I had thought about it, and I kind of filed it away somewhere in my mind, right? And so then when I started looking at the physics, serendipitously, that thing clicked later when I said, what do I have to look at in the early universe? Fluid flows, hydrogen flowing, right, in the universe, gas, not liquid, but gas, right? And so it was this weird kind of connection that I can explain to you now because I've thought a lot about, okay, where did that come from? Where did that come from? Where did that come from? I still can't tell you why that liquid was relevant to the gas that I was thinking about or whatever, but something about that, right? I was able to add into my calculation and say, okay, I need a vortex. I need something to go unstable. I need some really rapid sort of instability. So physics-wise, what I needed, that was a fluid instability. I needed a gas instability, for example, right? And so then I conjured up, from the physics, I figured out, okay, all of these things have to happen. And if that happens, I can make a black hole, right? Then was the harder question of, are those conditions available in our universe? And can it happen? How frequently can it happen? And if it happens, what it would look like. That's all secondary, right? But that little thing, so this is what I mean by kind of serendipity. These connections and things that you don't even know are consciously informing your thinking process. But what allows you to do that is a certain openness of your mind, right? That you're constantly, and obsession. Right? You're obsessing about it all the time. Every time I was doing this Q&A with you guys, but this morning I was thinking about a problem that I'm working on, and I've reached an impasse. Like I'm not able to go past it, right? And today during the Q&A, when you guys asked me about, the wavelengths of light and this and that, suddenly something has clicked and I'm dying to go home and do that calculation. So, you never know what it is, right? And I can't explain. And I think this is the thing that I tell you, that this inexplicable thing that happens, we don't know if AI can do that yet, right? All humans, by the way, all humans can do this. It just takes training and a certain openness of your mind, right? And we also do this thing, these kinds of connections in very unconscious ways in other simple things in our life. Like we will learn something from a completely different domain and we apply it somewhere completely differently. And and they're not lofty things like a scientific theory or whatever, but they're day-to-day things, right? We all do it. We have this capacity to make these connections, but keeping that capability alive, right? And I think it's also intricately linked to this idea that I often talk about, which is important for young people, is that you have to learn to feel joyful about anything that you figure out. Right? It doesn't matter. It doesn't have to be a breakthrough scientific discovery, whatever. So if you are a student, and this is something I've had as a child, and I try to encourage this in as many young people as I can, which is, when you learn to, they teach you you learn calculus, you learn how to do a differential equation, how to solve it, right? Obviously, a million people have solved it before. You're not the first one. But when you figure it out and you solve it for yourself, you're like, darn, I know this now, right? I think there's a little bit of a joy in that. It's like, I figured it out myself. And then also when you do a derivation, right, they've taught you how to do it in school. And this is what I used to do when I was in school. We'd have a homework and they'll say, show blah, blah, blah equals blah, 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 right? And there's a standard way to do it. I would do it. And I would always need to have two other ways to do it. A new way to do it, right? I want another way to figure this out. And yeah, I would do my homework really fast, finish it, but then I wouldn't be done with it. I would still be thinking, okay, I want to do this two other ways. How do I do it? How do I think about this, right? I sit down deeply, think about, okay, what is another connection that I can use to come to the same inference, right? So I think that retaining this sort of, all children have this excitement and joy, haven't figured. I mean, you see an infant that figures out something and you see a smile on their face. We have that. We shouldn't lose that. And as for advice to young people, I often tell young kids that I know who are starting college and stuff that, really need to build on your foundations. Learn foundational knowledge, because the foundational knowledge is what allows you to do this riffing, connecting that little vortex in the bathtub to the direct collapse of gas to form black holes, right? That riffing comes from knowing your foundations really well. Only then you can improvise and take leaps, right? And I think there's a real clamoring now for wanting to do research really early, like they're in 6th grade or 7th grade, they want to do research. Learn the fundamentals really well. And I feel that the kids who are now young people are so lucky. When I was young, many of you were young, we didn't have like 100 sources of information where you could learn from. You can now go to Coursera, take a free course on anything, go to Khan Academy, which I go to all the time, to teach myself something, right? We didn't have all of these ways of learning new things. And I think keeping that interest to learn a lot of different things, and that's what I think we should be using the internet for, like milking the internet for, is learning. And I think also feeling that, feeling free to choose what you want to do in your career and life, and and realize that science is an option, and scientific career.
Just two linked things. They take off from what Shubhajit asked you. Given the numbers in India, and you talked about the strength of India's skill and talent, is the JEE model the brutal competitive examination where you lose, where the bell curve doesn't get in?
Right.
Where do you see that playing a role in developing the next generation of science talent? Should we be looking beyond that? So that's number one. And two was a pure hypothetical. You've been in many universities. If you were to design the university of the future, next 50 years, so how would it look different from now?
Right. So, I mean, as for, India has a lot of challenges, and the challenge is a scale of numbers. So it's very hard to see how, what could be an equitable, fair way to pick talent and allow channeling of people to different fields. I don't really have an alternative, but I think what I feel bad about is this process of getting ready for some of these exams. It kills all the joy of learning in young people, and I think that that's very sad. So there's a way in which gaming those and getting ready for those has been very disruptive creatively for young people. Um, as for the University of the Future, so I think it was before the pandemic, MIT, which is my alma mater, they had a task force on the future of education. So I was on that task force. And they asked exactly this question: how would you imagine, what would your ideal MIT look like, right? So I was a very strong proponent of the fact that my vision for MIT and for any top future university, it would not have departments, it would have vertices. So there would be a vertex where different disciplines converge, because I think the future in terms of where the breakthroughs be in science or even in the humanities or social sciences, the breakthroughs in thinking, the ways in which we can transcend our cognitive limitations and come up with new ideas is going to come from interdisciplinary collaboration. It's not going to come from a siloed way of looking at the world. It's going to really come from looking at the world through multiple vantage points simultaneously, right? And I think that's going to be the power. So my idea of a future university will have vertices, knowledge vertices, and not departments. There wouldn't be these silos. So, even universities like Yale, right? So, I direct the Franke program in science and the humanities, which is the flagship interdisciplinary program at Yale. I mean, one could argue, why do you need such a program, right? You shouldn't really. People should be able to collaborate. But it's very hard the way professionalization, careers, career incentives, et cetera, are set up. Primarily funding is set up. It's very much along disciplinary lines. Coming back to one of your earlier questions about what you think philanthropy can do, one of the things that philanthropic support for sciences, for example, could do is really start to channel and push us towards interdisciplinarity. And I think a push from that direction of resources could be quite impactful and would cause the entire ecosystem to respond and change. I truly believe that interdisciplinarity is where the future is.
So last two quick questions before we end. Kaushik and I'm sorry, huh? Okay, please.
So I had a question. There's a study saying that Hubble telescopes now capturing pictures at 40% of streaks of images of satellites passing by. So do you think that also is affecting the ground telescopes now?
Yes. So I think the exceptionally large and unregulated number of satellites that are being launched are going to deeply impact optical astronomy for sure in the coming years. And it has not been great. At the moment, we are still able to remove these streaks with software and post-processing. But if there's a larger proliferation, it's going to be very hard. And I mean, I think I feel sad that, a young child in 100 years may not be able to see the night sky. But then, you know what? The way we are polluting the planet, we may not be able to see it anyway. So I don't know what to say.
Yeah. Kaushik.
Yeah. So I had one question, but I'm tempted to ask another one. The first question is that I take you back to your talk, what you said about the ecosystem, and related to what you were saying about knowledge as something which may or may not have immediate utility. How do you see society? Do you think it has regressed or progressed in respecting or appreciating knowledge which might seem abstract or theoretical? This is one question. The other question is about interdisciplinarity. You also talked about strong foundations. Do you think sometimes linearity attenuates
Absolutely.
foundations?
It's a great question. Yeah. No, thank you. They are both great questions. So your sort of first question about like the research sort of ecosystem, right? So, sorry, could you remind me what exactly you were asking me? That
So whether the society has
yeah,
progressed or
society has
regressed.
progressed. Yes, yes, yes.
Yeah,
Sorry.
in
Yeah.
terms of, knowledge which is not immediately
usable. Right, right. No, so I think we as an entire, we as a society and a culture have regressed in the sense that we have become very short-termists. A lot of that has to do with some of our technologies for global connection, social media and so on, that have reduced our attention span, and an overall kind of obsession with just our lifetime and not so much thinking about the next generations, right? I mean, we've been irresponsible with the planet. We've been irresponsible in our utilization of resources, air, water, everything, because we don't have that long-termism. We have shifted into this sort of short-term thinking and a mentality of return of investments, short-term return on investments. Yes, we need to move away from this short-termism and start thinking more long-term. So there's a foundation called the Long Now Foundation in the United States that I'm involved with, which is really focuses on long-term thinking, right? So they have a 10,000-year clock that as to just get people to refocus, to think about long term. Yeah, I think we have regressed, and I think we should make amends, and we should start making room and understand that some ideas, some work is going to be, we just need to look at history to see that, right? And I think we have to learn from that. And your second question about interdisciplinarity is a really good one. And I think it has to do with the fact that there is a little bit of tension with interdisciplinarity and this idea of competence and domain knowledge and anchoring in a discipline. And I think that you do need to be anchored in your training in a discipline to be able to then riff, right? It's like jazz. You have to learn how to play the instrument before you can actually improvise, right? So we will definitely need to have foundational knowledge that is, and that gives you domain mastery and competence. Those domains may also get a little redefined, right? So I think that's what will happen in the long term, right? So that I think what we define now as domain knowledge, for example, in chemistry, will also alter. So for example, astrochemistry, the understanding of potential molecules that lead to life and other in exoplanets, etc., right? That field of astrochemistry is very new, and that's going to become a very big field when we are going to have a lot more data in that. And that is interdisciplinary, it's astronomy and chemistry. And I think what will happen, as an example, I think over time, chemistry itself and astronomy itself will start to make that an integral part of their domain knowledge. So that astrochemistry doesn't become something that is in and of itself, so the domain itself will expand. That's what I'm hoping when I said those vertices, that those sharp definitions and boundaries will start to expand and blur. They will start to blur a lot more. Yeah.
Thank you so much. I think
Thank you.
that brings us to the end of the conversation. Thanks a lot.
Thank you so much.
Thanks for your time.
Thanks.